Hi, class. In this video, we're going to start chapter 4, which is one of the sort of big key messages, important topics of the whole course, where we talk about linear second order equations. So we've already seen some first order equations and how to solve them. In this chapter, we're only looking at linear versions because, like I've said a million times, nonlinear just gets harder. And so we're restricting ourselves to linear cases. And then we're going to break those cases down even further. But what I'm going to do in this video, section 4.1, is just kind of an introduction, and it gives a motivating example of where you see these types of linear second order equations. And that example is a mass spring oscillator. So here's the picture that we have. Let's say we have some mass on, a wheel or whatever that's pulling on a spring. And you can pull this out and it will sort of spring back and forth. Like that's obviously a thing you can picture. And the way that we model these types of physical things are, of course, F equals ma. So where is the m in this case? That's the mass of our, mass here. And what are the other forces that are at play? Well, we have our spring. So the force due to the spring is modeled by Hooke's law and is proportional to how far you have pulled out your spring. So that's y here, which is, this is our y-axis, how far out we're moving. And I'm going to put Hooke's law over here. And k is some proportionality constant that has to do with sort of it's the stiffness of the spring. And that's this term is negative because it goes opposite of the direction of the force. So another opposite direction would be due to say this wheel here. If it's causing a lot of friction, then it's going to slow down your springiness. So we have a force due to friction, which is, from physics, we can know that to be proportional to uh, just y prime to the velocity of your spring. So kind of the faster you're going, the more that friction will matter. And so that's modeled by this proportionality constant B, which is called the damping coefficient. Damping, and just phrase it, damping. Okay. And then we might also have, in this case, we don't have anything in our picture, but we also might have some external forces. Maybe you have someone pulling, a horse pulling on this mass, or someone going up and messing with it, or whatever it is. So you have, these are the three kind of main forces that you get on your system. So let's put this all together. We have ma. Well, a is our acceleration, so this is y double prime. So we have my double prime equals the sum of all of our forces. So we get negative ky minus by prime plus, we'll just call this f external. Or another way we can write this is my double prime plus k, oops, that's not what I want to do. I want to do my by prime plus ky equals f external. So this is our second order equation here. And we can observe that it is linear because it doesn't have anything kind of wacky going on with the y's. F external is independent of y. So think about what we know about these types of systems. What do springs look like? one thought might be that it looks like a sine function, right? Because especially if you don't have any damping, if you just have like sort of a frictionless spring, it's just going to go up and down and repeat over and over and over. So let's consider this case a little bit more. So let's assume that there is no damping, like I just said, and no external forces. So then we have our equation my double prime plus k y equals 0. And we're going to guess a solution, y of t equals sine of omega t. Then we can calculate our derivatives. Y prime is omega cosine omega t, and y double prime is negative omega squared sine of t. So next we plug in, and we get, so we're plugging into the red equation. So we get negative m omega squared sine of omega t. Sorry, this was sine of omega t there. Plus k sine of omega t equals 0. So our guess, y equals sine of omega t, is a solution when this equation holds. So we would need, if we combine these sine terms, we'd get k minus m omega squared equals 0, or omega equals the square root of k over m. Because k and m are given to us. So that, I mean, that makes a lot of sense. There is a sine function with that satisfies this equation. And if m is bigger, that would make omega be small. And so this number here in a sine function, if that's small, that means that the period is bigger. So that makes sense that the bigger mass makes the spring oscillate slower. And conversely, if k is bigger, then the period is smaller, and that makes sense too, because you've got a stiffer spring and it's not going to oscillate as far. Okay, so that's sort of a guess at the situation where you don't have any damping. So what if we do have damping? Now you would expect that you would have a sine function, but you'd be sort of slowing down, or your oscillations would get smaller as time goes on. So let's think blue. What are some solutions to, we're still going to ignore the external forces. We're going to ignore that for a few sections. So my double prime plus by prime plus ky equals 0. So I'm going to give two examples here, and they both differ just by b, which is the damping term here. And so we can imagine that, you know, maybe we have some sort of spring where you have a little bit of damping. So you start off like this, but you're getting smaller and smaller and smaller and smaller. And that's what happens in this case. And a function that can sort of damp off a sine wave ends up looking like y of t. You could use a cosine too also. And so I'm just going to give the answer you can check, let's see, you can, if you plug this in, take the derivatives and, combine like terms and everything like that, then you get that this is an equation. And that's what this looks like here, where this is kind of, the cosine is never bigger than 1. It's always between 1 and -1. So you're always like sort of stuck in between, this function here and then the negative of it, and you just flip up and down. So that's what these types of functions look like. Now in this case, it turns out that a solution to it is y of t equals e to the -5t, which is just an exponential. And so this is what's called an overdamped case, because there's so much damping that it just sort of kills your spring right from the start. So this is just sort of to give some intuition about how that damping term can affect your solutions. In addition to how we saw in the previous example of how your K and your M could impact what your solutions look like as well. And I'm not going to do any examples of one where you have external forces, but you can also imagine how that's going to do all sorts of wacky things depending on what those external forces are. And so that's a case that we're going to consider in a few more chapters. Not chapters, in a couple of sections. Okay, so as we wrap up this introduction, I'll just kind of summarize and say that generally we're interested in equations that look like, I'm not going to use the spring terminology anymore because we are not necessarily going to be talking about springs. That's just a motivating example. So A y double sum plus B y times cy equals some function independent of y that does have a apartment of grade C. So A, B, and C are constant, and our F is given. Because F is not what we're solving for. Y is our, and what we have. So these are called second order ordinary differential with constant coefficients. It's the constant coefficient that is really the simplification that we're looking at. Remember with the linear equations that we have in first order, sometimes what we do multiplying by the y or the y prime is add some e. And in this case, we were saying that we only want to think about and that's going to be the first simplification that we So in the next section, in section 2, we're going to consider F equals to 0.